Okay, dear students, let us see what is there in this question. A mass of 1 kg of water is brought to its boiling point of 100 degrees C using an electric heater of power 1.6 kilowatt. The mass of 0.86 kg of water remains after it has boiled for 200 seconds. So it was starting with 1 kg of water and we are boiling it. So we want it to boil to 100 degrees centigrade, and this much of the power is required. We are having that kind of heater. After 200 seconds, the time is also given. It is given that 0.86 kg of the water remains, and the rest of that is obviously converted into steam. The electric heater has two identical resistors connected in parallel. So this resistor is R, this resistor is R. The circuit transfers 1.6 kilowatt of power, which was actually required when switch A only is closed. It means that only A is closed, and the power loss here, which will be I square R, that will be corresponding to 1.6 kilowatt. The external voltage is 220 volts. So this is the external voltage. The molar mass of water is 18 gram per mole. So this is the molar mass of water. Yeah, of course we know it, because the water molecule is H2O, oxygen is 16, hydrogen is 1. So 1 plus 1 is 2. So 16 plus 2 is 18. Estimate the average speed of the water molecules in the vapor produced. Okay, so this is the first question, and we are now going to concentrate on this. So obviously, you try to understand this thing. When there is a liquid that we have, and we are boiling it, and so it is converted into, let us say, steam. Until and unless 100% of the water has been converted into 100% of the steam, the temperature does not change. That is a condition there. So we were having 1 kg of water, and some part of it, like nearly 0.14 kg of the water, has been converted into steam, but rest of the water is still in the liquid phase. It means that the temperature of the complete mixture is just 100 degrees C. It is not 110. It cannot be 120. Simple, straightforward. It has to be 100 degrees C. It means that the steam that they're talking about, like the vapor that they're talking about, the temperature of that is 100 degrees C, which becomes 373 Kelvin, isn't it? Because we would be adding 273 to add, and in every of the calculation we are only using Kelvin as a unit for the temperature. Anyway, so this is done now, and 18 is the molar mass that is given here. We want to find the average speed. Fine. So I can give you a direct formula for the average speed, but that formula is not given in the data booklet, or it is not even given in the books. So that is why, like, it's very easy. You can derive it and you can remember it also. As per paper one is concerned, that formula is very handy. Anyways, so I'm going to give you the derivation first of all. So what is written in our books? It is written that first of all we are going to find the average kinetic energy, which is given by 3 by 2 kBT. So this is the formula that is given in the data booklet also. So from here, we are going to find the velocity. We are going to isolate it. So half mv square, where m is the mass of one molecule and v is the average velocity of one molecule. So this is equal to 3 by 2. Kb is the Boltzmann constant. We can use that value, or we can even substitute it as the universal gas constant divided by Avogadro's number into the temperature in Kelvin. Now, here is the catch. The answers and your books, what they are doing is they're using the value of kb, and they first find the value of kinetic energy, and then they equate it with half mv square, and then they try to find the value of the velocity. But what I am doing is I am creating the formula for the velocity for you. Just a moment. So v square is equal to 3rt divided by m into Avogadro's number. Now be very careful here. M is the mass of one molecule, and Na is the Avogadro number, like number of molecules in one mole. So number of molecules multiplied by the mass of one molecule is equal to the total mass, that is equal to the mass of one mole of the gas. It means that it is the molar mass. Molar mass means mass of 1 mole of the substance, and that is already given as 18 gram per mole. So this becomes the mass. So 3RT divided by capital M is V square. So this velocity is actually average, and average is written as RMS here. This will be 3RT divided by M square root. There you are. We have the formula in our hand. Now we just need to plug the values here, and we can find the answer. Let us see. 8.314. Temperature will be 373 Kelvin divided by molar mass, which is 18 grams. But we are not going to substitute the value in grams because it is not SI unit. But the molar mass is always given in grams. Be careful at this thing. Molar mass will always be given in grams. We have to convert it into kgs every time. So that will be 0.018 kgs, and we are going to take the square root of this value. This is going to be our answer. So let me do this for for you on my calculator, and let us see what is the value that I'm getting. Yeah, so I am getting the answer as 719 approximate. Yeah, this is the average velocity of the molecules in the vapor state. Do you get it? Now, try to understand, like when I say average, so the kinetic energy, when I say average, it is actually the mean. So it is not written RMS, it is written average. And if we say average velocity, it will be RMS every time. It will not be mean. So there is no confusion here. Don't feel like why is that and what is that. It is like that. Velocity is taken root mean square, and it is still known as average. And the average kinetic energy is only a mean, arithmetic mean, but it is also known as the average. So this is how we do the first question here, and let us see what is the answer given in the mark scheme. So my answer is 719 meter per second. Okay, so the Mach scheme is here, and the velocity is coming out to be 720. So there you go, my dear students. This is the way that we do this question. Just a moment. State one assumption of the kinetic model of the ideal gas. So for the ideal gas, we have so many of the assumptions there, and you have to just use one assumption there. So the first assumption is kind of that the size of the molecules is very tiny, and you can say that there is no concept of the potential energy. We just assume that the intermolecular or interatomic forces are zero. They are not interacting with each other, and so the total volume of the molecule is really very small. They're tiny in size. So there are many assumptions. Okay, so you can just use any, and you can even see the mark scheme. No doubt about that. Let us now move to the next question here. Estimate the specific latent heat of vaporization of water. State an appropriate unit for your answer. It means that now we want to find the latent heat of vaporization of water. So what is the latent heat of vaporization? Q is equal to M into L. This is the heat which is required, which is to be given to the water if you want to convert it into steam. So it is given that 0.14 kg of the water has been converted into the vapor. So this is the mass, latent heat we want to find. So we first need to find what is the heat that was given to it. And it is given that the heater was on for 200 seconds. The power is given as 1.6 kilowatt. We are just assuming that only one resistance is firing, B is open, and A is closed. And in this case, the power is 1.6 kilowatt, and obviously, so the total energy will be kilowatt multiplied by time, which is 200 second. So it will be 1.6 into 1000 into 200. This is the total energy that is given to the water, and this will be equated with M into L. It means that the latent heat should be given by divided by 0.14, which is M. And so we are going to find the value of L from this. Okay, so let us try to find this value with the help of the calculator. So 1.6 divided by 0.14. Yeah, so I am getting a very high value that should be high, and the value that I am getting is 285,714 approximately. So this much of and what will be the unit for latent heat? You can see the unit will be joule per kg. So I am writing it as joule per kg. Now this can be written as 2200 kilojoule something. Approximately it will be 2200 kilojoule per kg, and which is actually the correct data. So we are finding the approximate value, so it is almost the approximate value. So this is how we do the third question here, like estimate the specific latent heat of vaporization. But let us first verify it from the mark scheme. Let us see what is the answer given. So I am getting this, and this is the method that we have done. So we are going to verify what they have done in the mark scheme. Okay, so where is the mark scheme now? Yeah. So state one assumption, and there are so many assumptions, you can choose any. And the latent heat is, yeah, they're kind of getting the same thing. 1600, which is 1.6 kilo, multiply by time, which is 200, and dividing by the total mass. So this is what they get. And exactly this thing is what we are getting. So they have taken the unit as joule per kg. As I've already told you, it is joule per kg. You can convert it into kilojoule per kg also. That is your sweet will. Okay, so the question number three is also done. So we are going for the question number four now. Okay, one, two, state the kinetic energy. Yeah, this is the question that we are now going to do. Explain why the temperature of the water remains at 100 degrees C during this time. So there's no kind of like, fine, we would be giving the explanation because that is what is the question, but I just wanted to say that there is no explanation for that because the phase is changing, and during the change of phase the temperature does not change. And why the temperature does not change, just listen to this. Like when it is in the liquid state, the molecules are basically closer together. They are attracting each other. There are some forces which are known as van der Waals forces, and the students, those who are in chemistry, they would be understanding what van der Waals forces are. Like for example, this is one molecule of water, this is another molecule of water. So this hydrogen and this oxygen, they start attracting each other. These bonds are like very weak bonds. That is why they are just freely still they are freely moving. So these are like wonderful forces. They are very weak forces, but anyways, this is how the fluid moves. So these bonds have to be broken. So when it becomes a steam, so these molecules are no longer interacting with each other, and the wonderful forces are kind of tending to zero at that time. So the molecules are just like moving with the random velocities. So we need energy to break the bonds. So when we talk about the latent heat, so latent heat is the energy, like it is the energy that is given to the liquid. This energy is used to break the bonds, but this is not the energy which is used to give or increase the kinetic energy of the molecules. No, the kinetic energy of the molecules is not increasing technically, mathematically, or in the ideal state we can say, but the bonding is breaking. So it means that something is happening at the end of potential energy rather than the end of kinetic energy. So we can say that yes, potential energy is increasing, so you're giving the heat, potential energy is increasing, but that is only in the case of real gases. Because we are concerned only with ideal gases, we are not even considering the potential energy. So you can just talk about it theoretically to give the reasoning. That is your sweet will again. So that is why the temperature of the liquid is not going to rise, and it is always going to be 100 degrees C. Let us see what is the explanation that they have given in the mark scheme. Okay, it is always good if you read the statements given by them, and if you're getting a similar question in your examination, it is always advisable to take their statements and write there. So do not try to rephrase the statements by yourself. Okay, so explain why the temperature remains this. The energy added is to increase the intermolecular potential energy of the particles, as I have told you, or break the bonds. I told you both of the reasons. Yeah, and this is the reason that I have given you. So accordingly, you can write it, and that is it. Let us now go for the next question, which is question number five. Yeah, it is here now. So the heater is removed and a mass of 0.3 kg of pasta. Now heater is removed altogether, and the mass of 0.3 kg pasta at negative 10 degrees centigrade is added to the boiling water. Determine the equilibrium temperature of the pasta and water after the pasta is added. Other heat transfers are negligible. Specific heat of the pasta is given. Specific heat capacity of the water is also given. Okay, so kind of bit confusing question here. Heater is now removed. Heater is removed. The mass of this is added. Okay, so we can just assume that 0.86 kg of the water is there. Obviously, we are not going to consider the steam because the steam has gone into the atmosphere. So we are not talking about that. So this much of the water is maintained at 100 degrees C, and what is the weight of the pasta? 0.3 kg. 0.30 kg of the pasta is added, and the temperature is negative 10 degrees C. So the temperature is negative 10 degrees C. Now we want to find what is the final equilibrium temperature. So we can just assume it to be T. So in this kind of cases, like in this question, this topic is given a specific name and which is known as calorimetry. Calorimetry is that branch of science which deals with these kind of questions. And what is the principle for calorimetry? The heat lost by a hotter body is equal to heat gained by a colder body. So, what is the heat lost now? So, heat lost will be mc, the specific heat of water, which is 4200. We are not going to use kilos there. We have to convert it into joules. So, mc delta T. So, 100 minus T, it's not final minus initial. Try to understand it is always higher minus lower, and we are only concerned with the positive values. That is why we are going to use higher minus lower. So this is the QL and the heat gained. Similarly, we can find the heat gain now. So this is 1.8 kilo, so it will be 1800 into T minus 10, so it will be plus 10. And mind it that I am not converting the temperatures into Kelvin. And why I'm not doing that? Because when we are talking about the difference of the temperature, it doesn't matter whether you're talking in the terms of Celsius or you're talking in the terms of Kelvin. One is the same thing. So these two should be equal to each other. Now, again, there is a lot of calculation here into 100 minus t. Okay, I think that I should be skipping the calculation because it is really going to be long. It would be taking time. So I'm skipping this thing, but we would be doing this thing from the mark scheme and we will see what are they doing. I believe this equation is 100% correct. No doubt about that. So let us see what are they doing. I think it was question number 5. Yeah. So they are again using the principle of calorimetry here. Yeah. So MC delta T. So 0.86 4200 100 minus T, 0.3 1800 into T plus 10. And this is the equation that we were working with, and this is how we do it. And so the equilibrium temperature is coming out to be 359 Kelvin, and the answer will be in the Celsius. You have to convert it into Kelvin because this T, everything is in Celsius, so you would be getting the answer in Celsius. So it is 86 degrees centigrade. We have to convert it into Kelvin by adding 273, and so the answer will be 359 Kelvin. Let us now move to the other questions. Oh my God, it's a really very long question. I must say, it's 20 minutes that I have been speaking now. Okay, so this is done. I believe only two more questions. Okay, so show that each resistance has a resistor of 30 ohm. Fine. So we want to find this. So that's kind of easy because the power output here is 1.6 kilowatt when only this much is connected. So the power will be given by I square R, or we just want to find the resistance here and the voltage is given. It will be better if we use V square by R, isn't it? So the voltage is 220 V square divided by the resistance R. And so this value is equal to 1600. And from here, we are going to find the value of resistance. So that is easy. We can do it with the calculator, no problem. Let me do it. divided by 1600. Yeah, I'm getting the value of the resistance as 30.25 ohm. And let us see if they are getting the same value, 30.25 in the mark scheme. Yes, exactly. They are getting 30.25. And because both of the resistances are identical, so we can say that both of the resistances are 30.25. Let us now think about the last question now. Question number 7. Okay, where are you? Calculate the power transferred by the heater when both switches are closed. So when both switches are closed, what is the power output? So power is like 1.6 kilowatt for one, and I think if both of the heaters are working, I think clearly it will be multiplied by 2. There is nothing to think about because the voltage is going to remain same, and so the power formula, which is V square by R, is not going to change. Neither the individual resistance is changing nor the individual potential difference is changing. It means that the power produced by one resistor is not changing. So 1.6 kilowatt will be produced by first resistance, 1.6 kilowatt will be produced by the second resistance. Overall, the total power output now will be clearly double. Simple. And so let us now verify this from the mark scheme again. And yes, you can see it is 3.2 kilowatt. As I told you, that we are just doubling the power. Whether the resistances are in series or whether the resistances are in parallel, the power is just added simply, just like arithmetic, P1 plus P2. Whether they are in series or whether they are in parallel, we find P1, P2, P3 and we just add them, whether they are in series or in parallel. So, my dear students, this is how we do this question, and I believe that I have clarified your doubts in this question. So, if there is any other feedback that you want to share, please share the feedback in the comment section. This is Professor Varun. Thanks for joining. Please share the video with all of your friends, and thanks for joining the YouTube channel. Bye.